Hello everyone, I'm J Wildberger. We're talking about music and mathematics together, and I'm introducing the idea of the chromatic scale as being really mathematically the fundamental framework for modern music, especially when we adopt a well-tempered or evenly tempered approach where the relationship between each of the semitones is the same. Okay, so this leads us to correspondence between the arithmetic of the musical scale, represented by the chromatic scale, and the familiar arithmetic of a clock, this sort of 12-fold pattern. So there's a beautiful parallel here. So we're going to call this clock mathematics and the 12-note scale, the chromatic 12-note scale. And it's this correspondence that we want to talk about today and the consequences of looking at this musical situation in a more mathematically natural and simple way. So we're going to see that there's some significant advantages allowing us to conceptualize things a little bit easier, actually to make calculations easier. And it turns out that there's also interesting ramifications the other way. So the study of music can actually lead to some insights mathematically. That's going to be a really interesting consequence of the discussion that we're going to have today. Okay? So we're thinking about a 12-note scale, and the notes of that 12-note scale just labeled 0 to 11. Okay, you can think about going from middle C up to the B, and then the next note back to a C. So there's a repetitive or cyclical aspect of this, represented by the repeating aspect of the octaves on a piano. Okay. Now, sometimes, to be a little bit more specific, we might say that this is note M0, and this is note M1, and this is note M2, etc. And I want to emphasize that the uniformity here allows us, and the well-tempered aspect of the way most instruments are arranged these days, in particular the guitar and the piano, allows us to think about this as representing not just the scale starting from C, but in fact the scale, the chromatic scale starting from any note. Right? So we could start with an arbitrary note, say E, and consider E to be the tonic or the reference point of view, so that E would be associated to the note M0. And then the successive notes marching up from E would get these further numerical names. So this framework here is a little bit, we're moving out from the usual framework, which is very much focused on absolute positions on the piano. There's middle C, there's the D above middle C, etc. And we're just looking at things in a more relative way, which is really more in keeping with the natural structure of things. After all, there is no God-given, central note in the universe. There's a natural translation invariance to the story. So when we adopt this sort of clock view of the notes on the piano or on a guitar, we're connecting very naturally, as we'll see today, with mod 12 arithmetic. Okay, so this is a kind of a variant of the usual arithmetic that one learns about in undergraduate mathematics, okay, where we sort of end up with a restricted kind of arithmetic, a smaller arithmetic than usual. And it's represented sort of geometrically very naturally by this clock arrangement. It turns out that we also connect naturally with a topic in mathematics called group theory. And I will at some point elaborate on the group theoretical aspects of this story. It's actually quite interesting. But today we're going to touch base with the mod 12 arithmetic. And I want you to firmly have this idea that this is just a representation, a different kind of representation of, say, notes on a piano. In particular, here's the usual setup. We can distinguish sort of where we are on a piano by the arrangement of the black keys. So the black keys come in a pair of two, and then a triple, and then a two, and then a triple, etc. And the note to the left of the two, that note right there, is note C. And for beginners, that's often sort of a starting point, sort of like the central note, if you like. Okay, so it's natural to associate this chromatic scale with the chromatic scale on the piano that starts with middle C. Okay, so then what we're doing here is we're just really naming the notes on the piano corresponding to the actual keys on the piano. Okay, we're naming them by giving them numerical values. Okay, so this would be note 0. Then this black one is note 1. Note 2. Black one, note 3. 4, 5, 6, 7, 8, 9, 10, 11. And once we get to 11, we've gone through 12 keys, and then we're back essentially at the same place that we started if we do one more step. So the next one is another note that's exactly parallel to this one, just one octave higher. And the relationship between the frequencies of these two notes is 2 to 1. Okay, so then afterwards the counting would continue in a cyclic fashion, 0, 1, 2, 3, 4, etc. And of course we could also go in this direction. Okay, so if we went 1 to the left of that 0, then that would be the same as going 1 to the left of this 0, so the next key over here would have name 11. Okay, so this is quite different from the usual nomenclature. Okay, the usual story is in terms of letters C, D, E, etc. And these black notes end up having names that are associated to the closest white notes with sharps and flats. And there's a kind of a duality. Sometimes we could refer to this as C sharp or as D flat, depending on the context. So that's a rather cumbersome notation. That's the standard one that's used in all of modern Western music. But it is a little bit arbitrary, and it's very much built up from the architecture, the physical architecture of the piano. What we're trying to do is step back from that and just look at the mathematical intrinsic structure, which is just represented by these 12 positions on the clock face. Now, in terms of a guitar, okay, well, the same kind of thing applies. We can associate these various positions to notes or positions on the guitar. And in fact, this gives us freedom. We're not really restricted to starting on any one particular string. Okay, so we could say start on say this low E, or maybe this A. Okay, let me do the A this time here. Okay, so this is the A key. A, usually it's A, B, C, D, E, F, G, A. But from our point of view, the names of these notes then, if we're sort of adopting an A-centric point of view, okay, so we're agreeing that that's going to be note 0, then this will be note 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then here's the octave, that's another A, so that'll be back to 0. Okay, so that's a basic kind of framework that we're going to be thinking about the chromatic scale as being sort of central, and that our notation for the chromatic scale is basically the simplest possible. It's just given by the numbers from 0 to 11, and then it repeats. Now, it may strike you as odd to have a mathematician sort of thinking about how we should structure music in a sort of an optimal or better way. But in fact, there is actually a long historical tradition of this kind of thinking. And I think it's interesting to look a little bit at the history of things. And in particular, this has actually a lot of implications for education. Okay, so there's, I think, a significant possibility of bringing mathematics education and music education a little bit closer together and having a little bit more synergy between these things. Because actually the musical structure and this discussion that we're having is actually providing motivation for some interesting mathematical things. Okay, so it's nice to have motivation to get students interested in learning mathematics, and students who are musically inclined or interested, which is a lot of students these days. Well, it's a natural way to funnel them into some interesting mathematics. Okay, so but if we go back historically to ancient Greek times, okay, already there was a very significant regard for music. And of course, that goes back to the Pythagoreans, in my earlier lecture, talking about this beautiful connection that they found between ratios of natural numbers and harmonic or intervals. So in ancient Greek study, there was essentially 4 aspects of mathematics. Okay, it was called the quadrivium. And the quadrivium, which sort of, encompassing mathematics, consisted of number theory, of geometry, astronomy, and music. Okay, it might be a bit of a surprise these days to think of music as a chapter of mathematics, but classically that's what it was. And that rough designation actually carried on for many centuries, even into the Middle Ages and into the European times. So in the Renaissance, music theory was very popular. So sort of abstract discussions of music along the lines that we've been talking about, having to do with various ways of tempering scales and intervals, etc. This was quite popular, and actually quite a lot of mathematicians ended up contributing to this basic discussion, okay, including some notable mathematicians. For example, René Descartes wrote a piece called Compendium Musicale in 1618. Mersenne wrote, Mersenne prime fame, wrote an important treatise called Traité de l'harmonie universelle in 1636. And I think he was perhaps the first person to really appreciate the importance of overtones, which is another interesting aspect of the story that we'll have to mention in a future video. But he was probably the first person to appreciate that. And then John Wallis, Euler, D'Alembert, all of these fine mathematicians wrote on musical theory. Okay, so, and other people as well. So there is a long tradition, not just of sort of informal connection between mathematics and music, but actually, mathematicians actually thinking seriously about the structure of music and how to organize and how to think about this. So what I'm doing here is really in the spirit of a long-standing interest that's been going on for a long time. Okay, so when we're studying music, it's not really the notes themselves which are so important, but it's combinations of notes. It's what happens when you bring notes together. So the relationship between notes becomes really of central importance. And so this is why the topic of intervals is crucial. And so let's have a look at this topic of intervals from this sort of mathematical, numerical point of view that I'm espousing. So we're going to measure things now in steps along the 12-note chromatic scale, because that's our basic reference point. So here we have our scale. We've chosen some arbitrary note. Maybe it's middle C, maybe it's E, whatever it is. And we're saying, okay, that's going to be note 0. And then going upwards, ascending, we've got notes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then back to 0. Okay, so we have these notes now, and now we can talk about the relationship between two notes. And the way we're going to do that, we're going to talk about steps, okay? In the obvious sense, going from one of these positions to the next one is a step, okay? Or more precisely, it's a one step, okay? So say going from 2 to 3, going from note number 2 to note number 3, we'll call that a one step. That's a one-step interval, if you like, okay? Say going from 8 to 10, that's a two-step. Going from 4 to 7, that's a three-step. And of course, calculating the step is not hard. You know the beginning and the end. You just take the difference. 7 minus 4 is 3. So to go from note 4 to note 7, that's a three-step. You take one step, 2 steps, 3 steps. Note here, going from here to here, we're also allowed to go around here, right? Because like on the piano, once you go from middle C to the next C, well, the notes keep on going past that. So once we get to 11, then the next one is 0 again. We're back to where the naming starts again, but the actual notes continue. So it makes sense to talk about the interval between this 11 and the next 2, okay? So we go from 11 to 0, and then from 0 to 1, and then from 1 to 2, so that's a three-step. Okay, so that's pretty simple. So now intervals are given numerical names. So now we have a numerical way of talking systematically about intervals. It's almost a trivial way, it's completely sort of obvious, but it is different from the current framework that we currently have. And so it does provide some advantages. So let's have a closer look at the comparison between this numerical kind of system and this more standard terminology. Okay, so here is a comparison, interval notation, this numeric notation that I'm proposing, and the standard notation which is used pretty well everywhere. So in this numeric notation, we have a list of intervals. The 1 step is the smallest non-zero interval. And then there's the 2 step, the 3 step, 4 step, 5 step, 6 step, 7 step, 8 step, 9 step, 10 step, 11 step. And then the 12 step would be like an octave. Now here are some examples of such steps with reference to these notes. Okay, the note M0, that's alerting us to the fact that this is a note. This is M0, it's note number 0. Okay, here's note M1, it's the very next note. So whatever our reference tonic note is, that's M0, going from M0 to M1, well, that's a step of 1. And an example of a 2-step would be going M0 to M2. An example of a 3-step is M4 to M7. 4-step M1 to M5. A 5-step M3 to M8. 6-step M6 to M0. Okay, so if we go 6 steps from M6, well, we go all the way up to M11, and then one more step, that might be M12, but we're agreeing that M12 is the same as M0. That's why we get a 0 there. A 7-step from M9 to M4. You're going up, okay? You go 9, 10, 11, and then 0, 1, 2, 3, 4. So that's a step of 7. Arithmetically, we can do the following way. If we take 9 and we add 7, we get 16. Okay? And then we recognize, well, going 12 is like going back to where we started. So that 16 is like 12 plus 4. Okay, so it's the same as note M4. And similarly, an 8-step from M11 to M7, you add 8 to 11, you would get 19. You can basically write 19 as 12 plus 7, so that's the same as M7. 9-step from M0 to M9, a 10-step from M4 to M2, an 11-step from M5 to M4. So these are all just examples of intervals of these kinds. Now here are more standard names for these intervals. So a 1-step is called a semitone. Okay? It's called a semitone because it's the 2-step which is considered sort of the standard interval, or the smallest sort of standard interval. It's because that's sort of an ingredient in the scale. When you go up the scale, you're more or less going up by tones, but not always. So the tone is sort of considered the simplest one on the way we write notes in the usual nomenclature with bars and lines. Then every step from one position to another is a tone. Okay, but from our point of view, it's the 1-step which is really the fundamental kind of step. You know, that's the simplest one. Okay, so it's a little bit unfortunate from our point of view that this semitone gets this sort of secondary name. Okay, it should really be a sort of the primary object from our point of view. So that's what we're doing. We're calling this the 1-step. So this is really the basic step. So going from M0 to M1, we can illustrate that with the standard notation if we, say, agree to take examples from the C scale on the piano, so that so the note that I'm calling M0 is C, and then the note M1 would be the next black key just to the right of that. That's C sharp. Or D flat, but we could say C sharp. An example of a tone, or whole tone, M0 to M2. So that if that's C, then going 2 would be D. So C to D, that's corresponding to this. 3-step is called a minor third. Okay, an example of that would be E to G. So in the scale of C, E is note M4 and G is note M7. Okay, so that's a minor third. A major third, M1 is C sharp, M5 is F. So that's an example of a major third, C sharp to F. A perfect fourth, that's like a 5-step. Okay, that's an example going M3 to M8. M3, we could say that's E flat. M8 is A flat. 6-step, that's exactly halfway to the octave. Okay, that's one more than a perfect fourth, so you could call it an augmented fourth, or it's one less than a perfect fifth, so you could call it a diminished fifth. So either of those names would probably be reasonable. And in this example here, that would be F sharp to C. A perfect fifth, okay, that's the usual name of a 7-step. Okay, so a perfect fifth, so M9, that would be A, M4 is E, so A to E is an example of a perfect fifth. And then one more than that, well, an augmented fifth you could call that, say M11 to M7, M11 is B, M7 is G, so that's an example of an augmented fifth. A major sixth, that's a 9-step, okay, going from C to A. An example of a minor seventh, that's like a 10-step, going from E to D. And a major seventh, that's an 11-step, just one less than an octave, okay, major seventh. That's an example of that would be F to E. So these are the standard names for these intervals, okay? And if you're a musician and you've been trained in these things, you're very familiar with these intervals, some of them more than others, okay? But like the perfect fourth, perfect fifth, major third, major sixth, major and minor thirds are crucially important in classical music, and in jazz music, the minor seventh and major seventh are also very important. Okay, so you would be very familiar. So if you ask a musician, what's a perfect fourth up from E flat, they'll whatever instrument they're playing, they'll be able to tell you pretty quickly that that's A flat. So, but I do just want to have these things juxtaposed, right? There's at least you can see some kind of advantages to this purely numerical system where the interval size between notes is easily read off just from the values of the notes themselves, and the actual names for the notes are sort of systematically and logically presented in the chromatic scale in the order that they come, and that the whole thing here is somehow more readily translational invariant. Okay, this is all based on C, these examples, but in principle you could apply this kind of framework quite easily to any scale or any tonic choice. Okay, so something to think about, the relative merits of these two systems. So I really want to emphasize this close connection between the geometry of a clock, a familiar clock, and this musical geometry afforded by the chromatic scale. So there's really a parallel kind of arithmetic here. And that's a happy thing because we're all quite used to the arithmetic of a clock. Okay, that's something we have a lot of familiarity with. So it's not such a big ask to just sort of transfer that intuition over to the musical setting. I think that's quite a nice thing for even students, primary school students, to learn about. They will learn about a clock, and at the same time they can be learning a little bit about music. So the actual mathematics of this is to do with mod 12 arithmetic. So that's the underlying arithmetic that is behind both the clock and the chromatic scale. So mod 12 arithmetic arises when we're moving along this 12-note chromatic scale. It's because we have a 12-note scale that this mod 12 arithmetic is crucial. So what is mod 12 arithmetic? Well, in a single sentence, it's simply this, that it's arithmetic with ordinary integers. All right, so that's like natural numbers and their negatives, 2, 3, 7, 49, minus 12, minus 79, etc. Those numbers, including 0. But with one additional rule. So all the rules are otherwise the same, the operations are exactly the same, but there's only one more rule that gives you mod 12 arithmetic from ordinary arithmetic. And that rule is this one right here, that 12 equals 0. Now I know in the regular world 12 does not equal 0, but let's just say that we agree that 12 equals 0. Whenever you have 12 of something, they're gone, vanished, 0. Well, so here then would be sort of the corresponding integer number line in that case, right? So let's say we start with this 0. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then here, where ordinarily would be 12, well, 12 becomes 0. Okay, so then we add one more to that 12, which is now 0, we will get 1 again. And then 2, 3, 4, 5, 6, 7. So it repeats until we get up to the next 11, and the next one is 0 again. So there's this then repeating aspect on this number line. This segment from here to here is repeated indefinitely as we go to the right, but also indefinitely as we go to the left. Right? So if you choose one of these zeros and you go 1 to the left, you're going to get 11. Just like over here. You go 1 left, you get 11. 1 left, you get 10. This is exactly just corresponding to moving around the clock, either in a clockwise direction corresponding to that direction, or an anti-clockwise direction going in that direction. Right? If you're at 12 o'clock, which is 0, and you go back, well, then you get to 11. You don't get to -1. Let me make that point here, all right? That's going to be a very important, interesting issue that will have all kinds of consequences for us later. So let me just remark, okay, that if this is sort of your 0, you're going left, you don't get -1, or, well, you do, but that -1 is really the same as 11. -2 is the same as 10. Okay, so some examples of arithmetic in this context. Well, 3 plus 6 is 9. So the usual laws of arithmetic hold. 6 plus 7 is 13. But I've written 1. Why do I write 1? Well, because 13 can be written as 12 plus 1. And the 12 is 0, so 13 is the same as 1. Which is sort of reflected here, right? Ordinarily 10, 11, 12, 13. That's where 13 ordinarily would be, but there's a 1 there. So if we go 6 from here, and then we go 7, 1, 2, 3, 4, 5, 6, 7. Yes, indeed, we do get 1. 1 plus 12 is 1. So if we go 1, and then we go up 12, then we get to this 1 as well. Or another way of saying this is 1 plus 12 is the same as 1 plus 0, because 12 is like 0. So 1 plus 0 is 1. Multiplication, 2 times 5 equals 10. That's just like ordinary multiplication. 3 times 5 is now 3, because 15 can be written as 12 plus 3. The 12 is 0, so we just get 3. 4 times 5 is 8, because ordinarily 4 times 5 is 20, and 20 is 12 plus 8. The 12 disappears, and we just get 8. Subtraction, 3 minus 2 equals 1, just as ordinary. But 7 minus 8, so we go 7, and then we go back 8. 1, 2, 3, 4, 5, 6, 7, 8. Well, we get 11. Or you could say, well, 7 minus 8 is usually -1, but we can add 0 to that. It won't change. So if we add 0 or 12 to -1, then we get 11. We typically like to get answers which are in this range from 0 to 11, because that corresponds to the positions on the clock, or positions on our chromatic number circle. 26 minus 4 is 10, because 26 minus 4 is 22, but 22 is the same as 12 plus 10, and so that's 10, etc. Okay, so that's mod 12 arithmetic, and that's really underlying the both the way a clock works, and calculations with a clock, and also calculations with the chromatic scale. Okay, so let's illustrate the usefulness of this numerical approach to musical notation by an example. We'll do the example in 2 different ways. So here's sort of a classical question. If you start on C, middle C, or any other C, and you go up a perfect fifth, and then you go up a major sixth, and then you go up a minor third, and then you go up a minor seventh, what note do you end up on? Okay, so let's write down the answer. So we're starting with C, okay, and then what do we go to? We're going up a perfect fifth. Okay, so you have to kind of know the intervals. So C, perfect fifth, that's up to G. Okay, G, okay, G. Okay, and then we're going up a major sixth. A major sixth. So from G, a major sixth is E. Okay, and then we're going up a minor third. A minor third. What's that? From E, a minor third would be to G. Okay, and then we go up a minor seventh from G. Minor seventh. So a minor seventh from G is F. Okay, so we end up on an F. Now I've been able to do that because I'm very familiar with the piano, so I can easily imagine, where we are, and I know that, a minor seventh from G is F, etc. Okay, But if you're going to calculate this, otherwise, it's not so clear how you're going to do this unless you have some pretty good familiarity with some musical instrument. So here is the same question, but now sort of transposed into this numerical language. So suppose we start on a C, and then we go up a 7-step. So a 7-step is the same as a perfect fifth. That's our new name for a perfect fifth. It's actually more representative of what's really going on. It really is a 7-step. It's an interval of 7 steps. Okay, so we've gone up a 7-step, and then we go up a major 6. What's that? Well, that's a 9-step. And then a minor third, what's that? That's a 3-step. Then a 10-step, that's a minor 7th. So what note do we end up at? Well, we're starting at note M0, okay? And then we go up, we're going up 7. Okay, I'm going to make the calculation like this. We go up 7, and then we go up 9, and then we go up 3, and then we go up 10. Okay, I'm not going to bother with all the intermediates because I'm just going to work with the arithmetic here, right? This is the same as M0 plus, what is all of this? This 7 plus 9 is 16, plus 3 is 19, plus 10 is 29. But the 29, maybe I'll write that, 29, okay? The 29 is the same as, because I'm working with mod 12 arithmetic, okay? So I can remove multiples of 12. So 24 is a multiple of 12. So if I remove 24 from 29, I'm going to get 5. So I'm really going up 5 from M0. So that means I'm at M5. So that's the answer. We start at M0. After all of this, we end up at M5. Now, if you translate M5 on the piano, 1, 2, 3, 4, 5, that is indeed F. So it does agree with the usual calculation, but we're kind of freeing it from the actual C scale. We're just making the intrinsic calculation, just adding up the various intervals that have been involved and using the mod 12 arithmetic, which is underlying things here. I'm J Wildberger. Thanks for listening.